Saturn's moon Titan has lakes. Not water, methane. Liquid methane at -290 degrees Fahrenheit. For years after their discovery, these lakes seemed still, glassy, smooth as mirrors, dead. Then, in 2023, scientists went back through old Cassini data, measurements from a spacecraft that died in 2017, looking for something they'd missed. And they found it. Waves. Ripples on the surface of Kraken Mare, a methane sea larger than the Great Lakes combined. Brightness variations suggesting tides on Ligeia Mare. Evidence of wind-driven chop on smaller lakes. Titan's lakes aren't dead. They're active, dynamic, alive with weather and tides and possibly forces we don't yet understand. And suddenly, everything we thought we knew about this alien world needs revision. In 2027, NASA will launch Dragonfly, a nuclear-powered helicopter the size of a car. It will arrive at Titan in 2034, and for 2 years it will fly, island to island, lake to lake, sampling the atmosphere, measuring the methane, searching for the chemistry of life in the most alien ocean in the solar system. This is the story of the only world besides Earth with stable liquid on its surface, and why those liquids might be moving for reasons more complex and more exciting than we imagine. Our solar system has over 200 moons. Rocky moons, icy moons, moons with thin atmospheres, moons with subsurface oceans. But only one moon has rain, rivers, lakes, seas, clouds, weather cycles, erosion. Only one moon looks like Earth. If Earth were frozen, toxic, and lit by a sun 100 times dimmer. That moon is Titan, Saturn's largest moon, bigger than Mercury, the only moon in the solar system with a thick atmosphere, and the only place besides Earth where liquids are stable on the surface. But those liquids aren't water. Titan's surface temperature, -290 degrees Fahrenheit, 94 Kelvin. At that temperature, water is rock-hard ice. Methane, natural gas, is liquid. And Titan has a methane cycle exactly analogous to Earth's water cycle. Methane evaporates from lakes into the atmosphere, forms clouds in the thick nitrogen-methane air, rains down onto the surface, fills rivers and lakes and seas, erodes the landscape, and evaporates again. It's a complete hydrological system, just with the wrong molecule. And that atmosphere is remarkable. Surface pressure, 1.5 times Earth's. Thick, substantial. Composition, 95% nitrogen, 5% methane, trace organics. The upper atmosphere is bombarded by ultraviolet light from the sun. That UV breaks apart methane molecules, creating complex organic compounds, tholins, that rain down as orange haze. Titan's sky is perpetual smog. The surface is dim, 1,000 times darker than Earth's daylight. But the air is dense enough for a human to fly with artificial wings. If you could survive the cold and breathe the atmosphere, which you can't, you could strap on wings and soar. Titan is weird, familiar yet utterly alien. September 1997. NASA and ESA launch Cassini-Huygens, a two-part mission. Cassini orbits Saturn. Huygens lands on Titan. 7 years later, July 2004, Cassini arrives, begins a 13-year tour of the Saturn system, and Titan becomes a primary target. Cassini will fly by Titan 127 times, closer than any moon has ever been studied. January 14th, 2005. Huygens separates from Cassini, plunges into Titan's atmosphere. 2.5 hours of descent. Parachutes slow the fall. And for the first time, humanity sees Titan's surface. River channels carved into the landscape. Rounded pebbles, probably water ice, eroded smooth by liquid methane flow. The landing site, damp. Methane-soaked ground, like a lakeshore after rain. Huygens transmits for 90 minutes, then its battery dies. But those 90 minutes prove something extraordinary. Titan has active surface processes. Erosion, transport, weather. This isn't a dead moon. As Cassini continues its flybys, radar imaging reveals dark patches in Titan's polar regions. Speculation. Could these be lakes? 2008. Cassini detects a specular reflection, a glint of sunlight bouncing off a perfectly smooth liquid surface. Confirmation. Ligeia Mare, a methane-ethane lake 420 kilometers across. Depth, possibly 200 meters. And it's not alone. Kraken Mare, 1,000 kilometers long. Larger than the Caspian Sea. Dozens of smaller lakes, river networks feeding them, shorelines with geological features. Titan has seas. But something was odd. The lakes were too smooth, mirror flat, no ripples, no waves. On Earth, radar images of oceans show texture, waves, wind chop, surface roughness. Titan's lakes showed nothing. Glassy reflections, perfect smoothness. For years, researchers wondered, why no waves? Several theories emerged. Hypothesis 1. No wind. Maybe Titan's lower atmosphere is calm, no wind to disturb the surface. But Cassini detected wind, measured atmospheric circulation. Titan has weather. Hypothesis 2. High viscosity. Maybe liquid methane-ethane is thick, viscous, resists wave formation. But the viscosity isn't that different from water. Waves should form. Hypothesis 3. Surface tension. Maybe methane's surface tension damps waves quickly. Possible but unlikely to explain complete smoothness. Or Hypothesis 4. We were looking at the wrong time, wrong season, wrong place. Maybe the waves were there. We just hadn't seen them yet. Titan has seasons. Its year is 29.5 Earth years, Saturn's orbital period. Cassini arrived during southern summer. Most observations happened in northern spring and summer. But Titan's weather is seasonal. Methane rainstorms concentrate near the poles during their respective summers. Maybe waves require specific conditions. Storms, tides, seasonal wind patterns. Maybe we just needed to look harder. September 2017. Cassini's mission ends. The spacecraft plunges into Saturn's atmosphere, burning up to avoid contaminating Titan or Enceladus. But the data remains. 13 years of observations, terabytes of measurements, radar images, spectra, atmospheric profiles. And in 2023, researchers went back through it, looking for something subtle, something they might have missed during the mission. Waves. The key? Analyzing brightness variations in specular reflections, sunlight glinting off lake surfaces. A perfectly smooth surface reflects light in one direction, a mirror. But waves scatter light, roughen the reflection, change the brightness depending on angle and wave height. By carefully measuring how the brightness changed across multiple flybys, at different times and viewing angles, researchers could infer surface roughness. And they found variations. Subtle, but real. Some measurements showed rougher surfaces than others. Some regions were smooth, others showed texture, evidence of waves. 2023 to 2024. Several papers published analyzing these findings. Detection of wind-driven waves on Kraken Mare during northern summer. Evidence of tidal influences on Ligeia Mare's surface roughness. Possible seasonal storm activity creating transient waves. Wave heights. Estimated at centimeters to tens of centimeters. Small, but definite. The lakes aren't dead. They move. Cause number 1. Wind. Cassini measured wind speeds on Titan. Typically slow, 1 to 2 meters per second at the surface. Gentle breezes. But during seasonal storms, winds can reach 10 meters per second or more. On Earth, wind generates waves through surface friction. Air moving over water transfers energy. On Titan, the same physics applies, but with liquid methane and a thicker atmosphere. The result? Small waves. Ripples. Nothing like Earth's storm-driven ocean swells, but enough to roughen the surface. Seasonal storms, methane rainstorms during northern summer, likely generate the most wave activity. Cause number 2. Tides. Titan orbits Saturn every 16 Earth days. Saturn's gravity creates tidal forces, pulling on Titan's solid body and its liquid surface. On Earth, the Moon creates tides in our oceans. Water rises and falls as the tidal bulge moves. On Titan, Saturn creates far stronger tides. The lakes should experience measurable tidal changes, potentially tens of centimeters. Tidal currents could generate surface waves, sloshing as the lake adjusts to the changing gravitational field. And the timing of wave detections correlates with orbital positions where tidal forces peak. Cause number 3. Subsurface activity. Beneath Titan's icy crust, 50 to 100 kilometers down, there's likely a liquid water-ammonia ocean. This ocean is heated by tidal flexing and radioactive decay. It might have convection currents. It's under pressure. If the subsurface ocean shifts, tidal sloshing, convective overturn, pressure waves could propagate upward through the ice shell. Those pressure changes could affect the surface lakes, create waves, cause sloshing. Speculative? Yes. But it might explain coordinated wave activity across distant lakes, something internal triggering surface effects. How do we know there's a subsurface ocean? Evidence 1. Tidal deformation. Cassini measured how Titan's shape changes as it orbits Saturn. The amount of deformation indicates a liquid layer beneath the crust. Evidence 2. Gravity anomalies. The way Titan's gravity field varies suggests internal density differences consistent with a liquid ocean. Evidence 3. Cryovolcanism. Possible water ammonia eruptions reaching the surface, sourced from the subsurface ocean. The most likely model? An ice shell 50 to 100 kilometers thick. A liquid water ammonia ocean 200 to 300 kilometers deep. A high-pressure ice core at the center. This subsurface ocean is potentially habitable, not for life as we know it on Titan's surface. Liquid methane is a terrible solvent for biochemistry. But the subsurface ocean? Liquid water, dissolved minerals, energy from tidal heating. On Earth, hydrothermal vents support ecosystems independent of sunlight. Chemosynthetic life using chemical energy. Titan might have similar conditions. Water-rock interactions, chemical gradients, energy sources. Could life exist in Titan's subsurface ocean? We don't know. But it's one of the most compelling astrobiology targets in the solar system. And here's the crucial link. The subsurface ocean might connect to the surface. Cryovolcanic eruptions bringing deep water ammonia slurries up. Methane reservoirs fed by deep sources. Chemical exchanges between the ocean and the atmosphere. If life exists in the subsurface ocean, could its chemical signatures reach the surface lakes? Could Dragonfly detect them? That's the question driving the mission. 2027. Launch. 7-year cruise to Saturn. 2034. Arrival at Titan. Dragonfly is unlike any planetary mission before it. It's a rotorcraft, a nuclear-powered quadcopter the size of a small car. 8 rotors, designed to fly in Titan's thick atmosphere. For 2 Earth years, 1 Titan season, it will hop between sites, flying tens of kilometers between landing locations. Starting point, Shangri-La, an equatorial dune field near the Huygens landing site. From there, island hopping toward the methane lakes, sampling different terrains, measuring atmospheric composition, searching for organic chemistry. Dragonfly carries a suite of instruments. Mass spectrometer, analyzing atmospheric and surface chemistry, detecting organic molecules, looking for biosignatures. Cameras, documenting terrain, geological features, lake shorelines. Weather sensors, wind, temperature, pressure, tracking methane weather in real time. Drill, sampling subsurface material, analyzing icy regolith. Each landing site, hours of analysis. Then, flight to the next location. Over 2 years, dozens of sites, comprehensive sampling of Titan's chemistry. On Mars, rovers travel slowly, tens to hundreds of meters per day, limited range. Dragonfly can fly 8 kilometers per flight, cover hundreds of kilometers over the mission. That mobility lets it visit diverse environments: organic-rich dunes, hydrocarbon sand, impact craters, exposing subsurface material, lake shorelines, methane-soaked regions, potential cryovolcanic flows, deep material brought up. And crucially, it can sample at the interface between land and liquid, the shorelines where chemistry gets interesting, where organic molecules concentrate, where reactions happen, where, if there are biosignatures, they might be detectable. Question 1. How complex is Titan's organic chemistry? We know Titan produces organic molecules, tholins, in the upper atmosphere. But what happens when they reach the surface? Do they react in liquid methane lakes? Do they interact with water ice at cryovolcanic sites? Do minerals catalyze reactions? Could Titan be making prebiotic molecules, amino acid precursors, nitriles, compounds relevant to the origin of life? Dragonfly will measure this directly. Question 2. Where does Titan's methane come from? Methane in Titan's atmosphere should be destroyed by UV radiation within tens of millions of years. But Titan is 4.5 billion years old. The methane should be gone. Yet it's still there, which means it's being replenished. Possibilities: cryovolcanism, bringing methane up from the interior. Deep subsurface reservoirs slowly leaking methane. Biological production. Unlikely, but not impossible. Dragonfly will measure methane isotopes, chemical fingerprints that reveal origin. If methane is primordial, left over from formation, isotope ratios look one way. If it's geologically sourced, they look different. This will tell us whether Titan's interior is still active. Question 3. Are there biosignatures? Dragonfly isn't a life detection mission, it's a chemistry mission. But if there are chemical anomalies, molecules that shouldn't be there, abundance patterns that suggest biology, it might find them. On Earth, life produces chemical disequilibrium, gases that react but coexist because life continuously produces them. Could Titan's chemistry show similar patterns? Probably not. But if it does, if there's even a hint of something biological, it would revolutionize astrobiology. And it would justify a follow-up mission, a dedicated life detection lander, maybe even a submarine to explore the lakes themselves. Dragonfly is just the beginning. If it succeeds, future missions become possible. Titan submarine, a nuclear-powered autonomous sub exploring Kraken Mare, measuring currents, chemistry, depth, sediment. Titan balloon, a long-duration dirigible circling Titan, studying global weather patterns and atmospheric chemistry. Titan lake lander, a stationary probe on a shoreline, monitoring waves, tides, and seasonal changes. Distant future? Human exploration? Titan's thick atmosphere and low gravity make landing easier than Mars. But the cold is brutal. Still, if anywhere in the outer solar system could support a human base, Titan is the best candidate. Saturn has 2 potentially habitable moons. Enceladus, subsurface ocean actively venting into space. Easier to sample, no landing needed, fly through the plumes. Probably more hospitable to life. Liquid water, energy, salts. Titan. Complex surface chemistry, organic-rich environment, stable surface liquids. Harder to explore, landing required, but richer chemical diversity. They're complementary targets. Enceladus for subsurface ocean life, Titan for prebiotic chemistry and surface processes. Both deserve exploration, and both will be explored this century. None of this would be possible without Cassini. 20 years ago, Titan was a blurry orange dot, a curiosity. Cassini transformed it into a world, revealed its lakes, its weather, its chemistry. And even years after Cassini's death, its data keeps giving. New discoveries, new insights, new questions. And in 2034, we'll return, not just to observe, but to touch, to sample, to fly. Titan is waiting. We used to think Earth was unique, the only place with liquid water, the only world with weather and erosion and dynamic surfaces. Now we know better. Europa has an ocean beneath its ice. Enceladus has an ocean venting into space. Ganymede has subsurface water. Even small moons like Mimas might have liquid layers. But Titan is the only world with stable liquids on the surface. The only place where you can stand on solid ground and watch waves lap against a shore. Not water waves, methane waves, at temperatures that would freeze nitrogen solid. But waves nonetheless. Those waves tell us something profound. Titan is alive. Not biologically, probably, but geologically, atmospherically, hydrologically. It has weather, seasons, erosion, transport, active processes reshaping the surface. And in 2034, when Dragonfly arrives, we'll see those waves up close. We'll sample the chemistry at the shoreline. We'll measure the wind that drives them. We'll trace the methane cycle from lake to cloud to rain. And maybe, just maybe, we'll find something unexpected, a chemical signature we can't explain, an organic molecule that shouldn't be there, a hint of something deeper. Titan has waves, and those waves are calling us to explore the most alien ocean in the solar system. This is Cosmic Canvas, where we map alien worlds. Until next time, stay curious, keep dreaming of distant seas.